All right. So, hello and welcome everyone to interactive live sessions for the course on CFD for incompressible flows. CFD means Computational Fluid Dynamics for incompressible flows. So, this course is being offered by NPTEL and being taught by Professor Amaresh Dalal from IIT Guwahati. Uh, my name is Debjit. I am a PMRF scholar and a TA for this course. So every week, every Tuesday from 6 to 8, we will be meeting here and we shall be discussing anything and everything related to the course. So this is the first week. This is week one. I'm sure that the lectures for up to week three has been uploaded. So in that sense, we are there is a delay between the lectures being uploaded and these sessions being held, and we will maintain that delay till the end. So starting today, every week we will have this up until week 12. Is that okay? Okay. So first of all, let me tell how we will conduct this courses. So of course, you will be going through the material every week, and you will have some doubts. So you can always ask those, and we can have a very open discussion about them. So those interactive live sessions, the interaction parts, if they are maximized, then that's the best. Other than that, to keep the discussion going, we will have some questions in front of us based on the material of the particular week that we were discussing. So today is week one, so we will be discussing some sample tutorial questions from the material covered in week one. Okay, so without further ado, let us begin. So this is question one for today's session. So first of all, read the question well, and I will be sharing a poll. You can select the correct option and put in your responses over there. So first of all, there is no hurry. There is plenty of time. Read the question carefully first, and then pick your option. So the question number one of today's session is: what is CFD used for? Option A: studying fluid flow patterns. Option B: designing new aircraft. Option C: developing wind turbines. Or is it option D: all of the above? So the poll is live. Preferably put in your responses in the poll. If you have some difficulties, let me know. Other than that, you can use the chat box, but try not to use it so that let's say if you solve it first and someone else is also trying to solve it, if they don't see the answer, then they will pursue it more honestly. So that way we can have a fair game, so to say. Okay.
How can I use a poll box?
Okay. So are you using a computer or a mobile phone?
Laptop?
Laptop. So but the poll should be okay. So there is one option you'll see in the bottom right hand corner. It shows three shapes: one triangle, rectangle, and circle. So select that. The poll should be available over there. Could you access it?
So what about for mobile phones?
In mobile phones also, you'll have to go to options, and there these icon for activities will be there. If you open up activities, you can see the poll. You can access it from there. Okay. So these are the ways you can access it anyway. So that's less important. More important is the content that we are discussing. So what is CFD used for? Is it used for studying fluid flow patterns, for designing new aircrafts, for developing wind turbines, or is it all of the above?
All of the above.
Yes, correct. So I'll end the poll now. So we have received one response in favor of option A and all of them in favor of option D. So indeed option A is correct, studying fluid flow. Okay, we'll look at the correct answer first. So the correct answer is D, all of the above. So indeed option A is correct, studying fluid flow patterns, but option B and C are also correct. So let's say if we're trying to design a new aircraft, so I'll try to draw aircraft. My drawing skills are not so good, but anyway, So let's say we are trying to design this aircraft. So there are many components where of this aircraft where the application of CFD finds its place. So first of all, you know that the aircrafts they fly in the air. While they do that, they face a lot of wind current in the upcoming direction. So basically, the wind is stationary and the aircraft moves towards the uh, moves in its specific direction. But you can reverse the problem and you can imagine that the aircraft is stationary and wind is flowing over it. So it's basically a change of reference frame, so to say. So if you do that, then we can find out the lift and drag forces which act on this aircraft. So lift acts in the upward direction, perpendicular to the direction of the movement of the aircraft, and it also experiences a drag force in the opposite direction. So, in order to move forward, the aircraft has to generate enough force so that it overcomes the drag, and it also generates sufficient lift so that it can stay afloat in the air. And then comes the next part. So you can imagine how does the aircraft generate this lift. So it has basically these wind turbines or gas turbines, sorry, not wind turbines, gas turbines located underneath the wings. And how these gas turbines work are that there are some blades in between, and it first of all intakes air that comes from the atmosphere. It sucks in. Then there is fuel being injected inside, an just like in an engine. And so this air mixes with the fuel, and then combustion occurs. So there also CFD also finds its application. So first of all, in generating this, in estimating this aerodynamic lift and drag forces, CFD is important. Then for modeling this very complicated combustion process which generates the power to sustain this, CFD becomes important. Indoor air quality, like the passengers who are sitting inside, and there is a air conditioning system in order to make sure that everyone is comfortable sitting inside. So there also the fluid flow patterns and the heat transfer patterns are very important. So these there are multiple such areas where CFD finds its application. So just within this small example of designing new aircrafts, CFD finds a ton of applications. Same thing for designing wind turbines as well. Let's say one single wind turbine, how much power will it generate for a certain rate of wind flow. In order to estimate that and optimal design of these blades and all, there CFD finds its application. And not only that, so usually wind turbines are not used as a single wind turbine. So there are basically large open fields where multiple wind turbines are there, and their spacing, how they will be spaced so that the energy generation can be maximized. These are all open questions which are relevant for academia as well as industries. So these are also places where CFD finds example. These are just few very small examples which we come across in this question. There are multiple other areas where CFD finds its application. Okay, so that's why this is a very important subject which we are studying and very relevant as well in multiple ways. Okay, so any questions? Always free feel to ask questions. These are interactive live sessions, so the interactions should be as much as possible. So the lectures are the I'll say this: the lectures will always have more content and more material from what we will discuss here, but we won't get a chance to interact there. Here in these sessions, here we can talk to each other. We can discuss anything, any doubts, any questions, or anything related to CFD. Okay. All right, so I'll assume there are no questions on this one, and we will move on to the next question of today's session, which is question 2. And question 2 asks us, what is the main difference between CFD and experimental fluid mechanics? So is it option A that CFD is simulation based while experimental fluid mechanics is physical equipment based? CFD is faster while experimental fluid mechanics is more accurate. Option C, CFD is more expensive while experimental fluid mechanics is cheaper. Or is it option D, CFD is more reliable while experimental fluid mechanics is less reliable? The poll is live. You can put in your responses in the poll. So there are multiple ways in which we can approach the study of fluid mechanics. So first of all, there is theoretical fluid mechanics. Then we have experimental fluid mechanics. And three, we have CFD or numerical way of studying fluid mechanics. So among them, so what is the main difference between CFD and experimental fluid mechanics? Is it option A, CFD is simulation based while experimental fluid mechanics is a physical equipment based one? Is it option B, CFD is faster while experimental fluid mechanics is more accurate? Option C, CFD is more expensive while experimental fluid mechanics is cheaper? Is it option D, CFD is more reliable while experimental fluid mechanics is less reliable? Read the question carefully, and once you have figured out the answer to it, you can put in your response in the poll. You can access it in the activities option that Google Meet offers. You can go there and put in your responses over there. So far, I can see only 5 responses. I would like to encourage all of you to participate in this and put in your responses. And if you need any clarification regarding the question, always feel free to ask. Okay. Take your time. There is no hurry. Think about it, and always try to clarify any doubts that you may have. Okay, so we will end the poll and look at the correct answer. So many of you have selected. Uh, okay, sorry. This is wrong. Okay, so actually, option A would be the correct answer, and here it is indicated that option B is the correct answer. That's not so. Option A is the correct answer. So why is it? Let's discuss in a bit more detail. So CFD is actually simulation based and experimental fluid mechanics is indeed physical equipment based. Option B is not correct. Why? Can anyone say why? Let's have a discussion here. Any guesses why option B is incorrect?
Because in experimental fluid mechanics there will be our man error.
Sorry, what? I couldn't get what you said.
Experimental any experiment there may be our human error.
Yeah, So that is indeed one way of thinking. Another way is CFD is faster. We cannot
Yeah,
always say this.
yes, CFD is faster compared to experimental, but the experimental fluid mechanics is not more accurate compared to CFD.
No, that's true. I'm raising this question as well. Is CFD always faster than experiments? Not so, right?
Uh, not always,
So,
because
yeah,
if you have simple, let's say, measure measure the flow pattern or to calculate the Reynolds number,
hmm,
whether it is in the laminar or turbulent, then we can go for the experiment also. For
right,
small experiment, experiment is faster.
right. So, basically, setting up an experiment and all that, those things take a lot of time, whereas CFD is indeed faster in that sense. But while actually running an experiment, CFD might take more time than the actual experiment being happening. Like, let me explain this with an example. Let's say we want to study. Okay, let's forget CFD for a second and let's look at, our philosophy would be any kind of experiment versus modeling. So let's say we have a ball and we put this ball in a wind tunnel where there is an incoming airflow and we want to calculate the lift and drag forces on the ball. So if we already have a set of wind tunnel and, some force detectors connected to the ball, then running this experiment would take very small time as compared to entirely simulating the uh, fluid flow around this ball and then trying to calculate the lift and drag forces. So in that sense, saying that CFD is faster always does not hold, right? But
Yeah.
yeah,
One more thing, sir, I would like to add in this.
yeah,
Sir, basically, when we are going for an experiment,
hmm,
it is more costly and expensive than the performing on CFD, like on any software.
right.
So I think it is much better to approach for a CFD rather than exactly for experiment.
Correct. So that's what point C talks about. So C here this is also an incorrect statement which says that CFD is more expensive while experiments are cheaper. But it's the other way around. Setting up huge experimental setup and equipment, those are very costly affairs, while CFD is very cheap. Like earlier, when computational power was not so much available, then computational cost was a very huge headache for people. But now, with the development of very fast computers and very cheap uh, processors, we have a lot of access to computational power, so that computational cost has gone down exponentially. So CFD right now is far cheaper than any kind of experiment that you can set up.
CFD, hello.
Yeah,
CFD is faster in case of testing a small, like you said, a ball.
yeah,
You want to test the ball,
yeah.
and if you are going to do that in 2D analysis,
Hmm.
so it is faster compared to experimental testing, isn't it? It is going to be faster.
Yeah, but
It does
not
not take.
always. That's the point I was trying to make. In many cases, CFD would be faster, true, but not in all cases. In some very complicated cases, it might so happen that performing a quick experiment would be much faster than carrying out a very accurate, very detailed CFD analysis of it. So you cannot say that it is always faster. Sure, in many cases it is faster, but not always. That's the point I was trying to make. Do you agree with me, or you have any?
Yes, it depends on the problem.
Depends on the
Mm.
problem. So if it's a very complicated problem and you are trying to do a direct numerical simulation with very small grid size and very accurate measurements, then it would take a lot of time. It would give. Okay, so in that cases, can anyone tell me what would be the benefit of doing CFD over experiments? So let me tell about the situation. There is a very complicated problem where experiments would be done quicker than performing a CFD analysis of it. But still, if someone does CFD, takes more time to do it, what additional benefit can CFD provide in that situation?
Oh, more accuracy.
Uh, See, accuracy depends. Like you can take very accurate measurements in experiments as well. And as far as reliability is there, experiments are always more reliable than CFD.
Sir, one thing as I can thought that when we are performing an experiment, it is for particular that time period. But if we run that particular situation in a CFD, then we have create a certain like coding and anything like boundary, its boundary condition. So we have a particular type of system. Then so we can run it again and in future when we required. So we can do this.
Experiments can also be repeated, right? So you're talking about repeatability and
Yeah,
reproducibility.
yeah,
So experiments can
yes, sir.
also, we can do that, right?
But if we see that repeatability of the experiments, experiments are far more expensive and time
Right.
consuming than a CFD. CFD will take only a single time. You can, I will say that one time investment of time,
No,
kind
but
of.
here I'm talking about a situation where CFD takes more time, right? This
Okay,
is an
okay,
exceptional case. So here, what
okay,
additional benefit can you have?
okay.
So you think about it, add some points. I will add one point. So let's say we have a very complicated sort of geometry and we have a flow through this. Many weird things are happening. So using an experiment, let's say in this situation you want to measure velocity profiles in certain locations. So in experiments, many points are not accessible. You cannot put in a pitot tube and make those measurements in all places. First of all, first point. But in CFD, you will get the velocity and pressure data over the entire domain. Okay, so this is one point that I'm making. Second point, uh, in order to make experimental measurements, we have to intrude into the system. Some sort of invasion has to be done. So there are basically experimental techniques are divided into invasive and non-invasive diagnostic techniques. So in invasive techniques, what happens is I intrude into the system. I take a pitot tube and I put it inside the system so that I can take velocity as a function of time measurements over there. But while doing so, I am actually disturbing the system. So can you understand that? So the system as it was behaving without the pitot tube, if I'm putting it in, it will definitely behave in a slightly different way. So that uh, change, that error which I'm introducing by taking the measurements, that happens in experiments, and that can be totally uh, removed if I'm doing a CFD analysis of it. Do you agree? So there are 2 points I made. Anyone wants to add any more points on the benefits of CFD?
Sir, actually, I want to add some more points.
Yeah.
The benefit of the safety is once when we do the experiment, only one parameter can be measured, only one condition can be analyzed once time. Then in safety, in different condition, we can run the different code in same platform.
Same. Sorry, I missed the last part.
The same computer and multiple computer, we
Right.
can use the
Exactly.
same. Yeah,
Exactly. So there the philosophy of parallel versus sequence comes. So
sequential.
yeah. So if I have an experimental setup with a certain number of input parameters, I fix them and I can only take one measurement at a point of time. So experiments have to be done in sequence. So forget about multiple parameters. I have only one parameter. Let's say some parameter x, which I am varying from 1 to 10 in steps of 1. So 10 experiments I have to do for x equal to 1, x equal to 2, x equal to 3, up until x equal to 10. So I have to do them in sequence, one after the other. But if I'm doing the same thing in a CFD study, I can use multiple computers, as well as in one computer I can take multiple instances and run them in parallel. So there I don't have to go from one to the next one, then the next one, then the next one. Not that way. I can do all of them at once. So this parallel versus sequence over here also, CFD has a additional benefit. Right? Very good. Anyone else? Any other point?
Actual flow visualization can be done in the CFD.
Right. So that's what I told earlier. Like actual flow visualization, what do you mean by that? Like the entire domain, I can visualize that in CFD, right?
Right, right.
Yeah. And in experiments, we are limited, so to say. So let's say one very important aspect over here, like CFD finds major application in spray technologies. So what are sprays? Basically, there is a nozzle and some liquid at a very high pressure comes and is released at a very high velocity. And due to flow instabilities and stuff, that spray actually the liquid jet that breaks up into small ligaments and then further down into droplets, right? So this is what sprays are. This is something that looks like this. So if I'm doing experiments, I have a spray and I have a camera. I'm recording the video of it. So while I'm doing this, I can only look at the periphery of the spray, only at the outside of it. What is going on inside, I really don't have an idea, right? If I'm doing experiments and taking a videograph of it. But if I'm doing CFD, I have access over the entire domain. So the interior parts which were not visible, they also become visible to me now. Did everyone get what I'm trying to say? So if I'm taking a videograph of this, I can only see the periphery, only the outside of what is happening here. What is going on inside, I have no idea. But if I can do a CFD study, I know the values in the entire domain. So I can take cutouts, sections in between, and look at them, analyze them, and try to understand what kind of physics is going on inside. Right? Okay. So anyone wants to say anything else, or should we move along?
In case of unstudy simulation, means CFD gives us any time step for measurement, like for 1 millisecond or 1 microsecond.
Hmm.
But for experimental, we have a limitation.
Yeah. So here I would
Means
like
we
to.
can measure the particular parameter at different, let's say 10 second, 20 second, that time interval.
Right. So you are correct, but I would like to add something on it. So the limitation of experiments is that I'm limited by the time step whichever measuring instrument I have. So if I'm taking a videograph, then my frame rate of camera, that limits me. Like so, if it's let's say 100 frames per second or FPS, then my time step is 1 by 100, right? So it's 0.01 seconds. But you're saying that we can take any time step for CFD. That is also not true. Like in CFD also we have discrete time steps, and we can uh, really get a benefit over experiments only if our computational time step is smaller than that. So what I'm essentially trying to say is, let's say my camera has 100 fps capability, so my time step through experiments is 1 by 100 seconds or 0.01 seconds. So using CFD, now in CFD, if I take a time step less than 0.01 second, only then I get that benefit which you are talking about, right?
Yes.
Okay, so good point. Yeah. Anyone else?
For design
Yeah.
optimization,
Hmm.
we can do easily in CFD, but more cost is involved in experimental fluid mechanics. You want to
Correct.
fabricate, if there is want to change your model,
Yeah.
again we cannot easily modify. You have to fabricate it again, and the money is involved. It is expensive, and then also again you have to go for a time for modifying the shape. So
Absolutely.
optimization can be done easily in CFD.
Absolutely. So this is included in point option C over here again. So exactly what you are saying, that if I want to change the design of an object, then every time I don't have to fabricate another model for bring it in and then conduct experiments on it. So I can simply change the geometry or any other parameter which I'm trying to optimize simply in a computer model. That would take less time as well as less expenses are involved in that. So in optimal design, CFD plays a very central role. Okay. Anyone else? Anything else? Okay. So we will move on. We'll move on to question number 3 of today's session, which asks us that what are the three main steps involved in solving a CFD problem. So option A is pre-processing, solving and post-processing. Option B is modeling, simulation and visualization. Option C is data collection, analysis and reporting. And option D is design, manufacture and testing. So read the question carefully, try to figure out the correct option and then put in your response in the poll. I can already see a few very quick responses. So we'll wait for the others. Everyone, there is no hurry. Do this correctly and try to participate in this. Don't just look at it in a one-way sense. So these sessions are supposed to be two-way, and so far the participation of everyone has been very good. So let's keep it rolling this way. Okay. So question number 3. What are the three main steps involved in solving a CFD problem? Is it option A, pre-processing, solving and post-processing? Is it option B, modeling, simulation and visualization? Is it option C, data collection, analysis and reporting? Or is it option D, design, manufacture and testing? If you have any doubts regarding the question, like if any part is not clear, then always feel free to ask. Unmute yourself and ask. You can type in the chat box as well. No issues. We have 8 responses so far. I'm hoping for more. Guys who are not answering, please read the question carefully, figure out the solution, and then put in your response in the poll. If you are unable to access the poll, tell me. We will try to access it. Like, I'll guide you how to access it. Okay, so we will look at the solution of this question. So it's option A, pre-processing, solving, and post-processing. So in CFD, these are the three main steps. So what actually goes on? So first of all, in pre-processing, what is that? So does anyone know what goes on in pre-processing?
Modeling machine.
Sorry, please repeat. I can't hear you.
No, modeling and machine, those things will be there.
Yeah.
Defining the inlet and outlet and the boundary condition.
Modeling and define the boundary conditions as well.
So the first step is to define the geometry. Right. So let's say for a pipe problem, we mentioned that one cylinder we will be using as our geometry, the dimensions of it, what is the radius of it, what is the length of it, right? So defining the geometry first is the first step. Then we will go to meshing. So we know about grids and meshes, right? So this entire spatial domain of the geometry that we decide on, that has to be divided up into smaller domains. So if I'm going ahead with this example, so I will break this entire thing up into small grids like this, and in this direction as well, right? So then we will solve the governing equations at each nodes and cells and so on. So meshing is the second step. Then in the third step, model selection. This is a very important step where human intervention or human expertise comes in. So as scientists or engineers who are trying to perform a CFD simulation, their understanding of the physics of the problem, that comes in over here. So here you have to decide whether you want to do a steady simulation versus unsteady, depending on the problem. So there are many problems in both industry as well as academia, where there are indeed some unsteadiness, some transients going around, but after some time it becomes essentially steady. There are indeed some variations, but those are not significant. So in that case, I can easily approximate the problem as a steady problem and still get reasonable results. So there are some cases where these variations are not insignificant; they become quite significant. So over there, picking a unsteady model is more appropriate. So selecting what is appropriate and not appropriate, this is where your understanding of the system comes in. So first of all, steady or unsteady. Then you'll have to pick the actual physics models, whether to consider laminar or turbulent, whether to include energy equation or not. So let's say if we're simulating a simple pipe problem, flow through pipe problem, energy equation is not required over there, right? But in a in a different scenario where, let's say, in a journal bearing, there also fluid flow takes place, but there, due to the very high viscous forces, energy is generated, and that energy in turn might affect the properties of the fluid itself. So there you cannot really exclude the energy part of it. So whether to include that or not becomes an important question. Then okay, so this is also a very fundamental thing, whether to do a 2D simulation or a 3D simulation. So let's say we will go back to this pipe case. We can do a full 3D simulation of it. That would be computationally more expensive, or we can use a bit of our head, and we can say that there is a center line going through the pipe, and the entire thing is symmetric about that center line. So in that case, what will I do? I will only take you know half the geometry of it. So it will go from 0 to r, and I will have the length whatever I've chosen here. Sorry. And then I will assume that this is axisymmetric and do a simple 2D calculation on it. So you can see that I transformed this more complicated problem to a more simplified one using some physical judgment. So this is a very important skill, a very important human skill to in CFD already most of the work is done by computers, and the rate at which artificial intelligence is evolving, these model selections and meshing and geometry part would be easily done by machines very soon. At least I hope so. But this model selection part, this is where the human creativity or human understanding plays a role. So if you do want to secure your careers in future, this is the part where you should improve your skills. So okay, so in pre-processing, we first of all select the geometry, meshing, model selection. Then finally what we do, as some of you already said, we define the boundary conditions. Sorry, we define the boundary conditions and the initial conditions, and then we okay, so another thing is we select the solution procedure or the solution schemes. We will, so the basic principle of CFD is we have governing equations, which are PDEs or partial differential equations. We convert them to algebraic equations through discretization, and after doing that we solve them using the computer. So while solving, I can use multiple schemes for solving these algebraic equations. So selection of that is these this solution schemes. So all these are part of pre-processing. Okay, any questions on this? No, right? So all this goes into pre-processing. Then during solving, this is the part. Simply the solution schemes which we selected during our pre-processing part, they will be used to solve it, and most of this is done by the computer itself, and we simply have to monitor whether the error is going down with iterations or not. Right. So if the error goes up, that means the solution scheme which you have chosen is wrong somewhere. It is, so the solution is diverging, and it won't give a proper solution in the end. So we have to look for decreasing errors. So this is where the maintenance sort of goes in. So once your computer is running, you have to monitor it and make sure that everything is working fine. So this is the solving part, and once we have solved, we get some numbers. We have to visualize that in the post-processing part. So basically after solving, what do we get? We get these huge matrices of numbers. So they have to be converted to some beautiful images so that we can analyze the fluid flow and have a physical sense of it. So our human brains are not good at interpreting numbers, but pictures we can interpret very well. So that's where this post-processing comes in, where we visualize the solution which we obtained after going through so much. Right? Any questions, anyone? Anything you want to say? You can unmute yourself and we can have a discussion on this. Did I say anything wrong? Can you find out any mistakes in what I said up until now? Always do that, okay? So as we are going through this, if you see any typo in the slides, or if I misspeak anything or interpret anything wrongly, always don't hesitate to interrupt and tell that. Okay. Any questions, anyone? Any doubts? Anything? Nothing, right? Okay. So then we will move on. We will move on to question number 4 of today's session, which says, which is not a way to discretize partial differential equations in CFD. Is it option A, finite volume method? Is it option B, finite element method? Is it option C, finite mass method? Or is it option D, finite difference method? So I'm talking about 4 different methods here. So you'll have to pick out which one is not a way to discretize partial differential equations in CFD. We have some very quick responses. Let's hope everyone participates in this and selects the correct option. There is no hurry. Take your time, read the question carefully, and pick out the correct solution. Which of these is not a way to discretize partial differential equations in CFD? Is it option A, finite volume method? Is it option B, finite element method? Is it option C, finite mass method? Or is it option D, finite difference method? Okay, so we will end the poll. Most of the responses are in favor of option C, which is indeed the correct answer. Finite mass method, which is not a way to discretize partial differential equations in CFD. Uh, so let's talk about the methods which are indeed ways to discretize. So first of all, we will look at finite volume method. Here what we do is we take a cell, or let's say in the entire domain, we will pick this small volumes, finite volumes. We know the dimensions of it, so dx and dy. So this I'm doing in 2D. In 3D also you can imagine you can have a sort of cuboid sort of like this with a dz as well, right? Simple thing. So we try to analyze the fluid flow within it. So I'll rub off this part. So within this finite volume there is a velocity coming in, some velocity going out, there might be some velocity coming in, there might be some flow going out. We will analyze this. We will apply continuity equation on this. We will apply Navier-Stokes equation on this and try to find out the. We will try to solve the exact values of velocities and pressures within this control volume, this small finite control volume. So this is what is meant by finite volume method. Finite element method, this is something that I don't know much about, at least in reference to solving CFD problems. So basically, in finite element method, finite, you know, very discrete mass points are taken, they are assigned some weights, and then those are solved. Finite element methods finds vast application in solid mechanics. Right. And for solving CFD problems, finite volume method and finite difference method are the more popular ones. And what we do in finite difference method is that, so in comparison to finite volume method, where we considered, a cell, a volume within which we solve it. So in finite difference method, what we do is we divide up the entire domain into a grid sort of like this, and we solve for the values in specific nodes only. In nodes like this. So these are basically points, not finite volumes. So what we do is we take the differences between neighboring points and then try to discretize the partial differential equations and solve those discretized algebraic equations. So that's the philosophy behind finite difference method. So in this particular course, the major part of it will be focusing on finite difference method only. Towards the end of the course, we will learn finite volume method as well. Okay. So throughout most of the course, the emphasis would be on finite difference method only. So this is what we will focus on and learn more. Okay. Any questions, anyone? Any questions, any doubt, any kind of clarifications you may want?
Does Taylor's equation is an example of finite element method?
What? Sorry?
Taylor's equation
Taylor's equation?
is an example of a finite element method.
Not really. Taylor's equation, it can be, Taylor's equation is used to, define derivatives of certain points, of certain values. Not derivatives, like if there are, so what does Taylor series tell us? So let's say if I have some value at I plus 1, I can say that it is I plus, dou f, dou x, anything. X could be any variable which f is a function of into some del x at I plus dou 2 dou f dou x square at I then into this square and so on. So Taylor series is applied in many of these finite difference, finite volume, finite element method. In all the methods, this Taylor series finds its application, but Taylor series itself is not finite element method. What you are asking? Does that answer your question?
Yes, yes.
So we have a question in the chat box. Will we learn how to solve? Sorry. Will we learn how to solve finite difference method? Yes. That's exactly what we will learn in the upcoming lectures. You uh, keep following the lectures. We will cover finite difference method in great detail. We'll learn how to solve heat equations in it, how to solve flow equations in it, right? All that we will learn. And a little bit of finite volume method as well towards the end. Okay. Anyone else? Any other question? Anything you would like to say? All right. Okay. So we will keep moving on. We'll move on to question number 5. So question number 5 is asking us uh, which of these is not a regular structured grid. So there are two important words here. One is regular, one is structured. Which one of these is not a regular structured grid? Is it option A, Cartesian, option B, cylindrical, option C, spherical, option C, triangular, option D, triangular, sorry. So the poll is live. You can put in your responses in the poll once you have figured out the correct solution to this question. Meanwhile, you guys keep answering. There is one question in the chat box where FDM is used. So FDM is one of the techniques to solve for fluid flow as well as heat transfer. So there are multiple applications where FDM is used. Countless, so to say. So an example, let's say there is 1D heat diffusion through a rod like this. This is a metal rod I've taken a candle and I'm heating one end, let's say some T equal to TH, and there is this other part. This is cold one at T equal to TC. So you can imagine, right? So if this is X, this is T, there will be a high value of TH here, and then it will decay down to TC here. So this is how the physics of the problem would be. What we can do is we can discretize it into multiple points, and then using FDM we will discretize the governing equations for this, which will be the temperature diffusion equation. We will solve this and find out the temperature variation to it. So this is one very simple example of FDM. There are multiple ways in which it can be used. We will see in the upcoming lectures. If you go through them, there will be multiple examples where we will use FDM to solve problems. Okay, so I hope that answers your question. Anything else? So moving back to our question at hand, question number 5 of today's session. Which of these is not a regular structured grid? Is it option A Cartesian, option B cylindrical, option B spherical, option C spherical, or option D triangular? So let me ask some more questions over here. What is a structured grid, first of all? What does structured grid mean?
Those finite volume will be separated equally.
Uh, that's not the correct answer. Structured grid. What does structured grid mean? It would not be equally spaced as well. Like you said, and someone in the chat box also said, equally spaced.
A
That's
grid,
not what structured grid.
a grid generation with the help of quadrilateral element.
Quadrilateral elements only.
Yes. Mm.
Structure grid can also have the well pattern
Well
structures.
pattern grid. Okay, so that's one way of saying. So the pattern of the grids will be the same all over the domain. Right? Anything else? What comes to your mind when structured grid comes? Okay, so structured grid basically means the pattern would be same, as someone said. The pattern would be, sorry, the pattern would be same. Right. So how many ways can the pattern be held constant? Okay, so most of you have responded. We will look into the solution for this one. The solution is option D, as most of you have responded. Triangular grid is not a regular structured grid. Okay, so structured grid basically refers to these three ways: Cartesian, cylindrical, and spherical. So we will look at Cartesian and cylindrical, for example. So let's say I have a rectangular domain like this, and I break up this into smaller grids which are rectangular as well, right? For it being structured, they do not have to be equally spaced. That's not a criterion. Equally spaced is taken care by this word, regular. Regular means equally spaced. So this is approximately a regular structured grid. I can similarly draw an irregular structured grid. So what I can do is I can have very close spacing over here, and as I move out, I can have wide spacings like this. Similar thing I can do here. So if I look at grid 1 and grid 2. Grid 2 is structured but irregular. 2 is regular as well as structured. Got the difference between the two? Right? Okay. So now we will look at something different. We will look at a cylindrical coordinate system. So I'm doing it in 2D only. So I will break this up into angular locations like this and circumferential locations like this. Give me a second. Right. So this again is a structured one, and my drawing skills did not permit, but you can equally space them, and in that case it would be a regular structured one as well. So okay, so we will try to differentiate between structured and unstructured. So let's say if I have something else which is like this, so we'll take a very simple example. Let's say I have a domain like this, and I'm discretizing points like this. So I have points, let's say I comma j here, I plus 1 j, I plus 2 comma j, and here same thing, I plus 1 comma j. Sorry, this would be I comma j plus 1, I plus 1 j plus 1. This would be I plus 2 j plus 1. Agreed, everyone? So basically, if I have a structured grid like this, and I have, sorry, and I have, say, point I comma j here, and some point I plus 1 comma j over here, and another point I comma j plus 1 here, I know the spatial locations of it. So here our coordinate system is like this. So x in this direction and y in this direction. So I know that the difference between this is in only delta y, and over here this is in only delta x, right? So if I know the coordinates, let's say of this particular point, so I comma j, I know the x and y coordinates of this point, and I know what delta x and delta y is. So then if I'm asked what would be the coordinates of I plus 1 comma j plus 1, what will be the coordinates of this? Anyone? Let's see who can answer this. I know that it's a equally spaced structured grid like this. What would be the coordinates of this point I plus 1 comma j plus 1? It would be
Yes, delta X.
plus delta x, y plus delta y, correct?
Yes.
Right. So can you say the same thing in this unstructured grid? Sorry. Unstructured. So if you know, let's say the coordinates of this point I plus 1 comma j, can you predict what will be the coordinates of I plus 2 comma j? No, right? But once again, in cylindrical coordinate as well, here also we know that the angular spacing is delta theta and the radial spacing is delta r. So over here also, if I move from any point I comma j to I plus 1 comma j, I can simply add delta r to it, and I know that theta will be the same in this way. So there is a certain pattern, certain structure associated with the grid points themselves. In unstructured grid, this is not there. Does this make things clear? Any questions, anyone? Can you do the same thing for irregular structured grids? This one? Can you?
No.
It may seem no, but actually, there is still that underlying structure associated with it. So moving from any point I comma j to I plus 1 comma j, I know that the difference would be in delta x only, and that delta x is not equal in case of irregular grid, but that data can be given to us. Like we can specify multiple delta x's going from delta x I to delta x I plus 1 to delta x I plus 2 and so on. So in this way, we can actually do that. In that case, delta x won't be a constant; it would be a you know
Multiplication or
values,
something.
some matrix. It would be. But if they are known, I can always do that. But in unstructured grid, the coordinates of each x and y for each I comma j would have to be stored. So unstructured grids, they have a more memory requirement while doing the calculations. Does the difference make sense to you? Could I make this clear? The difference between structured and unstructured grids. Okay, so there is a question in the chat box. I and J point is known to us. I'm sorry, I don't understand your question. Can you elaborate a bit? What do you mean by I and J point is known to us? You can type in the chat box, or you can, if you feel comfortable, you can unmute and ask as well. It's up to you. Meanwhile, any other questions, anyone? Any doubts regarding this? So basically, in the memory location for regular structured grids would be the minimum. For irregular structured grids, it would be a bit more, since delta x and delta y are not constant, but they are multiple values. And in unstructured grids, the coordinates of each grid point has to be stored separately. So the memory location allocation would be the most. Okay, so related to the question in the chat box, I and J point is known to us, parameters is known or not. So yeah, that's the point which I was trying to make. So here, if we consider parameters as the position of it, the location of it, x and y coordinates, then in order to know the coordinates of each and every point in an unstructured grid, we have to store those values somewhere. So we cannot simply calculate from knowing the value of the neighbors. But in case of structured grids, we can always calculate that value if we know the neighbor value. Does that make sense? So each and every point's value does not have to be stored. We will look into this later. We will see that structured grids are more easy to understand, but unstructured grids, they have their benefits, which is why they're used. So in a very complicated geometry, that cannot be discretized into structured grids. So their unstructured grids have to be used. They allow us to model complicated geometries, but they come with this additional problem of memory allocation. But once we sort that out, it allows us more flexibility. We can solve more complicated problems using unstructured grids. Okay, so I will come back and make a more important point. So Cartesian is this one which I showed. Cylindrical is this one, and similarly there could be, you can imagine a spherical coordinate system, right, which is you know I'll try to draw and do some justice to it. I don't know how far my drawing skills would permit. So something like this. You can imagine a globe which has latitudes and longitudes like this, right? So it's a very poorly drawn image, but I hope you get the idea. So a spherical coordinate system, uh, a spherical structured grid can also be used, but triangular grids won't turn out to be regular, won't turn out to be structured. Why? Let's say we take an example. Let's say we do something like this. I have triangles. You get the point, right? So here if I have I comma j, where will I plus 1 comma j be? It could be here, it could be here, and then also in order to find out the location of it, I need to know the exact coordinates of them. I cannot simply add delta x or delta y, pre-known values of delta x or delta y to get those points. Understood? So that's why triangular elements cannot be used to make regular structured grid. They have to be Cartesian, cylindrical, or spherical. Okay. Any doubts? Anyone? Any questions on this? Feel free to ask. No, right? Okay. So we will move on to the next question. We will move on to question number 6 of today's session. So the question is, select the correct form of the general transport equation. There is a general transport equation which we learned about in the lectures in week 1. So what is the correct form of it? There are 4 equations given in the 4 options. Carefully look at them and find out which one is correct, and then put in your response in the poll. The poll is live right now. So the terms are basically the same. So it's dou t of rho into phi plus the gradient of, okay, not the gradient, so to say. So this is del dot rho u vector into phi plus equal to the third term is del dot gamma into del phi. This is the gradient of phi plus some s phi. These are the 4 terms, and they are constant across all the options as well. So it's the plus minus signs which are jumbled. You'll have to select the correct one, correct combination from here. So we already have a few responses in the polls. So let me ask some questions. So these individual terms, they have some meaning, they have some names. Can anyone name them individually? So I'll name this term 1, term 2, term 3, and term 4. Can anyone say what term 1 is? Dou t of something, rho phi. What do we call this? So there is one answer in the chat box, temporal term. Anything else? It has multiple names. It's also known as the unsteady term. the storage term, if we look at the physics of it, it becomes clear, like things are coming in and going out. Whatever is getting stored within a control volume, that is reflected in this term, dou dot T of that, with time that evolves. So if a particular physical quantity is stored, that would increase. If it's depleted, then this value would be negative. But it would be represented by this term only. So that's why it's called a storage term. Also another name is transient term. So this is what takes care of the transients in the system. So this is a term which has multiple names. So term 2, del dot rho u phi. What is this term known as?
Terms.
Sorry, can you come again?
Convection term.
Convection term. Yeah. Convection term, also known as advection term. So basically, this means that this particular value phi is convected or advected with a certain velocity u. The third term, del dot gamma into del phi. What is this known as?
Diffusion.
Diffusion term. Correct. So this term takes care of diffusion of any physical quantity. So let's say there is no transience, there is no convection, and there is no source as well. So the fourth term, this is known as the source term, right? So in absence of anything, if there is a physical quantity, by the mechanism of diffusion, it can spread out. So this term takes care of that, represents that diffusion, and this gamma is the diffusion coefficient. So we will look at different physical quantities and their corresponding diffusion coefficients. So if it's some species, then its particular diffusion coefficient is considered. If it's temperature, then conductivity is the diffusion of that. In case of momentum, viscosity is the diffusion coefficient, analogous to diffusion coefficient in that case. So this comes from the physics of the problem, and we will look into more details of this later. Okay. Okay, so I'll close the poll. Most of you have answered in favor of option A and a few in favor of option C. So if you look at the correct answer, option A is indeed the correct one. So we will have to look into the derivation of it in order to prove why option A is the correct one. I will try to give some physical arguments to try to prove this. So derivating it would not be permitted by the time that we have. So I'll give you some physical arguments. You can challenge them if you are not convinced. So the first term, the storage term, this takes care of whether the quantity within this goes up or not. Okay, so we will take a very simple example. So let's say this is our bank. Okay, we keep money in our bank. So every month, let's say we get some salary. That salary comes to our bank account. So that's how the balance within our bank account goes up. So that going up and going down, that can be taken care of this first term. And salaries coming in, and there are expenses as well. So that outgoing expense, this incoming salary or income minus the outgoing expenses, this would constitute what? This would constitute this advective term, right? So in advection, there are things coming in, there are things going out of your control volume, and similarly in the bank account example that we are taking, there is money coming in, there is money going out. Whatever balance remains is what contributes to the balance going up and down. Is that all? Is there any other mechanism in which your balance can change? Anyone? Any other way in which your balance can change without income and outgo?
If interest is added,
Right, correct. So interest being added, this also drives up. So this is what is represented by our source term. We will see that within the domain that we will solve for velocity, temperature, and so on, there will be some source terms which will increase those values. So from a physical argument, can you tell what is the source term for velocity? What increases velocity?
vortex.
Not really, it's pressure. So a pressure difference, to be more accurate. So if there is a pressure difference that drives the flow, and we will see that in Navier-Stokes equations, there is the pressure gradient is the source term over there. Similarly, in heat equations, there could be many ways. Can you guess some, like electrical flow within, let's say, a metal rod? That can be a source term. There can be chemical reactions, which can be source terms for uh, energy or temperature. So these kinds of source terms are there. And in our example, the interest that we accrue on the money that we have in our bank, that is a source term. And unfortunately, diffusion doesn't take place in bank accounts, or not unfortunately, rather fortunately, otherwise we will lose money to our neighbors or fellow account holders. But in the physics problems that we talk about, so let's say there is some energy, there is some temperature, higher temperature in one point, so that temperature would ultimately diffuse down to its neighbors as well, right? So this is how diffusion takes place, and uh, this particular term takes care of that diffusion happening. Makes sense? Any doubts, any questions, anyone?
I just want to add one thing that in case of bank, what you take scenario, there are inflation. It take as in diffusion, where it's reduce our purchase value of money.
Right, correct. Very good. So yeah, in that case, you can say it is diffusing out. But no, there is a catch over here. So in diffusion, this point is losing whatever physical quantity is there. The neighboring points are gaining this quantity. In case of inflation, everyone loses. No one really gains anything. Anyway, so this was a fun example which we looked at. Anyone else would like to say anything else? No, right? Then we will move along. We will move along to question number 7 of today's session. And this is a particularly important one. So, question number 7 says, what are the very high and very low Reynolds number approximations of the Navier-Stokes equations, respectively? So, respectively means the first one is the very high Reynolds number approximation, and the second one should be the very low Reynolds number approximation. There are 4 options given. Read them carefully. So, option A is Burger's equation and Bernoulli's equation. Option C is Euler's equation and Stokes' equation. Option C is Laplace equation and Burger's equation. Option D is Stokes' equation and Euler's equation. Which one would be correct? Read them carefully and pick out the correct one. So let me write down Navier-Stokes equation for you. Steady Navier-Stokes. Let's forget about the unsteady part for now. Or we can keep unsteady as well, no problem. In 1D. Okay. So dou u dou t plus u dou u dou x equal to minus dou p dou x. So there will be a minus 1 by rho in front, and okay. So we will look at the first case initially. So very high Reynolds number. Reynolds number very high. How can we write Reynolds number? Can anyone tell me? What is the formula for Reynolds number?
Rho VL by mu.
Rho UL by this mu by rho I can replace and write it as mu. This is okay as well, right? So very high Reynolds number, what does it mean? Either this numerator is very high or this denominator is very low. So if we consider this, that the denominator is very low, what does it mean? Okay, there is a physical significance of Reynolds number as well. It means, the ratio of inertia forces over the viscous forces. So this nu being very low means viscous forces being very low as compared to the inertial force, and that results in Reynolds numbers being high. So that means this diffusion term we can neglect in the first scenario. And then whatever we are left with, this is known as the Euler's equation. Okay. And the second case, very low Reynolds number, which means the inertia forces are very high. Very low as compared to the viscous forces. So this entire left hand side, this disappears and this term remains. So in that case, this term equal to 1 by rho dou p dou x. This is known as the Stokes equation. So option B we'll see is the correct answer. So basically, there are many situations which we will face where the Reynolds numbers are very high. In that case, if we ignore viscosity, our lives become a bit simpler. In that case, we will use that approximation. Remember very carefully that these are approximations. There is indeed viscosity still acting there, but those effects are not significant, which is why we can neglect them and still get reasonably good solutions. So in that case, we will forget about the proper Navier-Stokes equations and solve Euler's equations, which are technically easier to solve. Similarly, in very high viscosity regimes, so one example of this is creeping flow around some spheres. This was the first problem solved by Stokes, using this approximation. So that is called creeping flow. Very slow flow dominated by viscosity over a sphere. It can be any other geometry as well. So that limit of very low Reynolds number flows are known as Stokes flows. So very slow and viscosity dominated flows where Reynolds number are very low, those are called Stokes flows. The particular regime is named as a Stokesian regime. It's written as this Stokesian regime, you can say. So this is for very low Reynolds numbers. So option B here is the correct one. Euler's equation and Stokes equation respectively. Any questions so far? Anyone? Any doubts? No, right? Okay. So,
Hello.
yeah.
What is burger equation?
What is Bernoulli's equation? So in Bernoulli's equation,
No, burger.
Burger's equation. Okay.
First burger is there. No?
Sorry, your voice is breaking up. What is Burger's equation? Is that what you are asking?
Yes. Hello.
Give me a second. Yeah, I heard you. Give me a second. My computer froze up a bit. Yeah, can you see the slides? For a second, I lost the slides. I'm scripting
Yes.
on this question number 7 slide. These are visible, right?
Yes, yes.
Okay. So we will go back to our initial Navier-Stokes equations. Okay, so here simply if the pressure there is no pressure gradient, then that is called Burger's equation. We can simplify this further if we neglect this term as well, the viscosity part, then that is known as inviscid Burger's equation. In that case, this simply becomes dou u dou t plus u dou u dou x equal to 0. Now, this is a very simplified case, but this is important. Why is it important? Let's say, forget the value that we are solving here. Forget that it is u. Let's say it's something else. Dou c dou t plus u dou c dou x equal to 0. What does this equation represent? Can anyone tell? What is this particular equation known as? We learned this in high school physics. This is basically the wave equation. So if there is a particular quantity c like this is x, this could be my time coordinate, and this is c. So wave like this would move along in time like this. So this can be represented by this sort of a equation, and this is known as the 1D wave equation, or not 1D, sorry, the wave equation of first degree. If we manipulate this a bit, so let's say we take dou c dou t equal to minus u dou c dou x, and then take a derivative with time. So dou c dou t, this becomes like this, and u, then we change the order in which the derivative is taken. So we put dou c dou t here, and this dou c dou t we plug in from here. We know that dou c dou t is equal to minus u dou c dou x. So what I get is there is already one u over here, another u comes in, and the minus sign gets cancelled as well, and this becomes dou 2c dou x square. So I'll write this neatly over here. So I have the second derivative with respect to time equal to velocity square into dou c square dou x square. This is known as the wave equation of the second degree. And these equations can be solved by a certain method known as method of characteristics. I will encourage every one of you to go back and Google this. You can learn it, and this method of characteristics is a powerful tool which was used for the first Apollo mission. So the Apollo 1 mission, when we did not have these advanced computers, as well as advanced schemes were also not present at that point of time. So then, using this very simple method of characteristics, the load calculations on the rockets were calculated. So it's a very powerful tool in that sense. It sent the first rocket, right? So this is something I will encourage all of you to go back and look at, the method of characteristics, which can be used to solve wave equations like the sort that we looked at over here. Okay. Anything else? Okay, so the initial question that we started with, what is Burger's equation? I tried to start with that. That part of the question is clarified, right? Does anyone have any other questions or any doubts regarding all this? If not, then we will move along. We will move along to question number 8. This is also very important. We have to match the following. So you can see that there are two columns. In the first column over here, in the first column, we see the names of multiple equations: Fourier-Bio equation, Poisson equation, Laplace equation, diffusion equation, and on the second column over here, we see actual equations in numbers like del square t equal to 0, del square t plus q triple prime over k equal to 0, and so on. So what you have to do is we have to match the four options in the first column with the second column, whichever you think is correct. And once you get the correct combination, you have to pick out the correct combination from the options given here. If you have any doubts, please ask. Anything you need to discuss, like we don't have to do each of these alone, right? We can have an open discussion and do this together. So, okay, one hint I'll give is that an easier way to do this would be to look at the second column first and pick out whichever is the correct name of the equation, instead of looking at the name first and then trying to write out the equation and matching it with this. So look at the proper written out equations first and then try to figure out what are the names of this. So we will do this together. So option 1 from first column is del square t equal to 0. What is this known as? What is the name of this equation? Anyone?
Is it Laplace equation?
Laplace. Correct. You also said correctly. Someone wrote in chat box. The option 5. We already have 1.
B. Diffusion. Third.
Yeah, what are you saying? Sorry, I couldn't. Can you please repeat? So we will look at the second equation now. Second equation is del square T plus Q triple prime
Poll
over
is
K.
not on.
Sorry,
Poll is not on.
pole is not on. Oh, sorry. Yeah, now it is live. Sorry, I missed it.
Yeah.
Once you figured out, you can put in your response in the poll. Meanwhile, let's try to solve this together. So option 2 from second column is del square T plus Q triple prime over K equal to 0. What is the name of this equation? Anyone?
Poisson equation.
Poisson,
Poisson.
Poisson equation. Okay, so the correct pronunciation of it is Poisson equation. It's not Poisson. Okay. So there was a French scientist whose name was Poisson. Okay. So anyway, you are correct. So option B from the first column matches with the second one. So B2. Uh, Now, if we go and look at the options, we can already figure out that B2 and C1. So option C would be the correct one. But let us look into it further. So for the sake of completeness, if we're in an exam, then our solution will end over here only. We won't waste much time over the next questions. But for the sake of completeness, we are learning here. So we will look at the other equations as well. So the third equation is dou t equal to alpha del square t. What is the name of this equation? Anyone?
Fourier Biot equation.
No, this is not Fourier-Biot equation. This is diffusion equation.
Diffusion.
Fusion equation.
This is diffusion equation. And finally, option 4, only Fourier-Biot equation remaining, which has all the three terms. The unsteady term, this is the diffusion term, and then the source term as well. This is known as the Fourier-Biot equation. Here also, pronunciation wise, it is not Biot. The T is silent. It is Fourier-Biot equation. This is option A. So what do we have? Option A 4, B2, C1, and D3. This perfectly matches with option D, which is indeed, sorry, option, I'm so sorry, which matches with option C, A4, B2, C1, D3, right? So, which is indeed the correct solution. So, option C would be the correct answer to this. Everything clear? Anyone, any question regarding this? Any doubt or any other question which comes to your mind? Like it could be tangential to the things that we are discussing as well. Okay. So now we will move on to question number 9 of today's session. We'll launch the poll. Okay. So what are boundary conditions in CFD simulations? Are they option 1, information about the fluid flow at the edges of the computational domain? Option B, information about the fluid properties such as density and viscosity. Option C, information about the fluid flow at this, sorry. Option C, information about the fluid flow at the starting time. Or is it D, all of the above? So read the question carefully. Once you have figured out the solution, pick the correct answer in the poll. Put in your response over there. The poll is live. We already have some quick responses. What are boundary conditions in CFD simulations? Are they information about the fluid flow at the edges of the computational domain? Is it option B, information about the fluid properties such as density, viscosity, and so on? Is it option C, information about the fluid flow at the starting time? Or is it option D, all of the above? If you need any clarification regarding any option, you can ask. If something is not clear, then we can elaborate it further. Okay, we have many responses. I'll end the poll over here. So most of them are in favor of option D. Only two in favor of option A, which would have been the correct answer. So if I have a computational domain like this, it is the information about the edges only that constitutes the boundary conditions. So information about fluid properties such as density and viscosity, these are, you know, these are information which I need to solve, but those are not boundary conditions. Boundary conditions are, let's say I'm specifying the u at this boundary, the u over here, the u over here, u over here on the four edges. That constitutes the boundary condition. So let's say in a coed flow like this, I can say that u would be equal to 0 in the two no slip boundaries here. Okay, I can give a fixed value of u equal to u naught, let's say, in the inlet, and in the outlet I'll get some velocity distribution like this. So these are known as boundary conditions. So that's why option A would be correct. So, and option C, information about the fluid flow at the starting time. Does anyone know what this information is known as? What are they called?
Initial conditions.
Correct.
It's called initial condition.
Initial condition. So for solving unsteady problems, in addition to boundary conditions, we will need this initial conditions as well. So this talks about the information in the entire domain at the starting time t equal to 0. As t progresses, we will solve and calculate the values over there. But in the initial t equal to 0, we have to give some fixed value to the entire domain, to the all the points within that domain. That is known as initial conditions. Does that make sense what I said just now? Because from the answers that you gave, I can see that there was some confusion because most of you picked all of the above. It's not all of the above, it's only the first one. Uh, does it make sense? Why? Are you convinced with the reasoning that I gave?
Can you please explain once again about option B?
Option B.
Yeah.
Yeah, so fluid properties like density, viscosity, heat capacity, and all that, those are material properties, but they are not boundary conditions. Boundary conditions are, the specification of the values which I want to solve at the boundaries. So in week 2 lectures, if you as you go through the lectures and learn more about those, so there you will see that the governing equations are partial differential equations, and from the theory of partial differential equations alone, forgetting about the physics, they have this necessity of some values being specified at the edges of the computational domain. So those are boundary conditions, and you'll see that some class of problems, they are sufficient with only boundary conditions. We will discuss this more on the next week, but now I'm just saying. So there are some classes of problem which need only boundary conditions. There are some classes of problem which need initial conditions as well, in addition to boundary conditions. So we will look into which classes need what later on. But okay, so I diverged a bit. Coming back to your question, the material properties, the fluid properties like density, viscosity, and so on, those are informations which you indeed require in order to solve it, but those are not boundary conditions. because density is in let's say an incompressible flow, density is not changing with time or space. That's a specific value that remains constant. You do not have to solve for density, you do not have to solve for viscosity, so we will not worry about those. But velocity we will have to solve for, and the velocity at the edges we have to know those. We have to have you know some pre-knowledge about those in order to solve them, and that knowledge is, that information is boundary condition. Could I answer your question?
Oh, yes, yes.
Thank you. Anything else, anyone? Okay, so we will move on. We are nearing the end of today's session, so this is last question from my side. So match, this is again a match the following type question. Match the following types boundary conditions with their mathematical expressions. So there are types of boundary conditions given in the left column: Dirichlet, Neumann, Robin, Cauchy, and in the right hand side we have different mathematical forms of it. So here also you have to match these with the name of the type of boundary condition. So again, let's do them together. So here also we will start with the right hand side. So A, we have dou y dou x equal to f. What kind of a boundary condition is this? Can anyone say?
It's to Newman.
It's a Neumann type boundary condition. 2. So in Neumann type boundary condition, what is told to us? Some gradients are told, some derivatives are specified. Right. So here also we are specifying the derivative of y with respect to x by some function f. This f could be a constant, this could be a function of time as well, that doesn't matter. As long as this gradient is specified, we know that this is a Neumann type boundary condition. Can anyone give an example where Neumann type boundary conditions are applied? Can you imagine sort of any kind of problem where a gradient at the boundary is specified? Let's say I have a wall like
In
this.
video, in class lecture, we have talked about the process of adiabatic process. That is, I remember. It's
Yeah,
adiabatic wall.
correct. So there is a wall like this. This wall is at a certain temperature T, and there is a ambient over here, ambient air at T infinity. So if this wall was adiabatic, if I put some, insulating material over here, there would be no heat flux, right? So this dou T dou X would be equal to 0. So here I am specifying this gradient as 0. So this is one example of a Neumann type equation. It could not be 0, it could be something else as well. So let's say I know that there is a specific flux coming out of this. So in that case, K dou T dou X would have to match that flux, and then dou T dou X would have a constant value, not 0, which was the case in adiabatic. So in this case also, this is a Neumann type boundary condition. Okay, so we will look at the second one. So y equal to f. Here the particular value is defined, not the gradient. What kind of a boundary condition is this? Can anyone say?
Dirichlet.
Dirichlet. So it's pronounced as Dirichlet. The T is silent, and this is Dirish, not rich. Okay. So please don't mind if I'm correcting you. I want you to learn the correct way to pronounce this. Okay. Yes, someone is raising a hand. Do you want to ask anything? No. Okay. So once again, what kind of a application or example area of Dirichlet condition can you think of? Any example?
Constant temperature at particular wall.
Correct. That is one way. Let's look at it. So I can say that a uniform fluid flow like this is coming from the inlet. Here also, what do I mention? So in this inlet, at x equal to 0, I will say that u equal to u naught. So what kind of a boundary condition is this? This is a Dirichlet type boundary condition, right? Okay. So we will move on. We'll look at option C, where C1y plus C2 dou y dou x equal to f. So this is what? This is a linear function of the value as well as the derivative, and that is equal to something. So what kind of a boundary condition is this? What is the name of this?
Proven mixed.
Correct. It's a condition also known as mixed boundary condition. Now also I will ask what is an application that you can possibly think of where Robin condition is used. We will go to our simple wall experiment over here. So there is a wall. This is convecting heat outside. This is the ambient is at some T infinity. So and there is a gradient over here as well of temperature. So basically K dou T dou I within the solid should be equal to the convective heat transfer over here, which is T minus T infinity. So, okay, there will be a negative sign here, and with some manipulations, we can show that H into T plus K into dou T dou I, H into T should be equal to H into T infinity. So see, this form we can find here, right? C1y plus C2 dou y dou x equal to some F, right? Makes sense? This example was given in the lecture as well. So if there are no questions, we'll move on to the last one where two equations are there. Y equal to F1 and dou y dou x equal to F2. And there is only one option left, which is Cauchy's equation. This is not something which was discussed in the lecture, but this is another type of boundary condition which shows up in some problems. So let's say if we look at a similar example, so let's say if at the boundary T is mentioned and dou T dou y is also mentioned, both are fixed. In that case, it would be a Cauchy's type boundary condition. Okay. Any questions, anyone? So the correct answer would be 1B, 2A, 3C, 4D. Which is the correct one? B, A, C, D. So option B would be the correct one. Option B indeed is the correct one. Okay. So that ends the questions from my side. If you have any questions, please do not hesitate to ask. Anyone, anything?
Sir, actually, the reference book are given too many in session. In this session, can you suggest that from which book we start for
See,
this
third
course?
will not follow any single book.
Yeah,
Uh,
yeah.
Different parts he will cover from different parts. So the first one, Tanhill, Fletcher, that one should have enough of finite difference method. and the book by S.V. Patankar on simple algorithms and so on. That should cover the finite volume part. Since most of everything that we are covering would be related to finite difference method, so you can start with the Tanhill-Fletcher book. Then later on, when finite volume is introduced, you can move to the second book written by S.V. Patankar. Okay. Anything else, anyone? Okay, so if there are no questions, we will close today's session. It has been great. Every one of you has been, very enthusiastic and participating throughout. So I expect all of you to continue this throughout the session. Okay. So, and always, if you have any feedback or suggestions to give to me, I'm, fully open to it. I will try to, make improvements as we go along. Okay. So, thanks a lot.
Okay, thank you.